Hey guys, these are some example problems that I created to help you all out with your multiple choice for this week. This week, as you guys probably already know, it's coming from the College Board. I'm not allowed to put those questions up for public viewing. I can only give them to you as an assignment to work on. So what I've done here is I've made up examples that are like the problems, and they, in particular, I try to make them like the problems in such a way that they are similar to those problems in the ways that make them difficult. So um, let's go ahead and get started. So example one here should help you do number one. Now, this is a related rate question. Now, whenever you are doing related rates, this part you don't need to write this if you don't want to, but there's some steps that we talked about. A lot of times what you're going to want to do is you're going to want to draw a picture first. Second thing you're going to want to do is when you do your picture, by the way, you want to label it. After that, you want to identify your given rate and your desired rate. After that, you find a formula that connects the variables. Then you take the derivative of that formula. Then you plug in all the known values and you solve for what you want. Okay, so it's kind of a 7-step process. A lot of times, by the way, units matter on these problems. But now this is usually what you do with a related rate question, and this is a related rate question. It's just that it's definitely presented a little bit differently. So, but these basic ideas will be present in most of the examples that I'm going to be working out for you. So let's go ahead and begin this one. It says the area of a triangle is given by this. So that's our step, what is that, 4, where you have to find a formula that relates the variables. A represents the area, B represents the base, H represents the height of this triangle. I'm going to go ahead and draw that. Now it doesn't say what kind of triangle it is, so it doesn't really matter what kind of triangle I draw. But I'm going to just make it a right triangle. But we have to be careful here. Just because I'm drawing a right triangle doesn't mean that you can just use Pythagoras Theorem just because you feel like it, because this is technically for any triangle. So if it makes you feel safer, you could actually draw a different triangle that is not Pythagoras Theorem, where that represents the height, this represents the base. Okay, so just know that you're not necessarily free to use Pythagoras Theorem here unless you have specifically a right triangle. Since the height usually does make, well, it always makes 90-degree angles with the base, you could do Pythagoras Theorem in here somewhere, but you just have to be careful. A represents the area, B represents the base, and H represents the height. Now what this means here is this is telling me that the rate of change of H with respect to time is the same thing as the rate of change of B with respect to time. What that means is that, let's say that H, the height, is growing, so that the triangle is becoming taller. Well, at the same time, the base is growing as well, and it's growing just as fast as the height is. So that means they have the same rate of growth. This is saying the rate of change of the area is equal to some constant number being multiplied by the rate of change of the base. So whatever the rate of change of B is, the rate of change of the area is that value multiplied by K, whatever K is. Now they're saying that if B equals 4 and A equals 36, find the value of K at that instant. Okay. So this problem is a little bit different than the steps that we usually have, because after we draw our picture, we identify the rate we want, and we identify the rate that we have. But this thing is just kind of weird because it's not asking us to find a rate, it's asking us to find K. So we're going to just skip right now all the way up to step 4, which is where you write out your formula. So we got step 1 here. We really couldn't do step 2 or 3 because it's just not that kind of a question, but we are going to move on to step 4, which is where you back up a little bit here and relabel this, where you write an equation to connect your variables, and they gave that to us. So that was nice enough. Now step 5 in the steps that I gave you is take the derivative of this thing. So if you take the derivative of a, you get dA dt. This over here is a product rule. So I'm going to treat the b, 1/2 b as my first element of the product, and I'm going to treat h as the second element of the product, and we'll go from there. So the way the product rule works is we have blank times blank, blank times blank. In the first set, we'll take the derivative of the b, so that's 1/2, and then since it's being with respect to t, we put dB dt. Okay, then we put h next to that without a derivative. That's the product rule. And continuing the product rule, now we keep the b part the same, and we take the derivative of h instead. Okay, so there is our derivative. Now we're going to start plugging some stuff in here. That's step 6. Okay, so we do know some things. So for instance, I know that dA dt is equal to k dB dt. So I'm going to replace dA dt with k dB dt. I don't know what dB dt is, so I'm going to leave that for now. No way to figure that at the moment. We can actually find h though. It doesn't tell us what h is, but we can find it. Here's how we can find it. We can come back up here to this original formula. They tell us that a is 36. They tell us that b is 4. So we should be able to find h. So if I divide both sides by 2, I end up with h equals 18. So a lot of times you will come back to this equation in step 4 to find a missing variable, and we can do that. So h is 18 plus 1/2 b. We know b is 4. And dH dt, we don't know what number it is, but we do know that dH dt equals dB dt. So I'm going to put that there. Okay, now I've got a huge mess I'm looking at, but I'm going to clean it up a little bit. So all I've done so far is steps 1, 4, and 6. Drew a picture, wrote a formula, took the derivative of it, and plugged in some stuff. Now we get to simplify our answer here from number 6 a little bit before we finish up. So we're going to have k dB dt on the left. Nothing I can do on the left. But here, this can be simplified. Half multiplied by 18 is 9. And half times 4 is 2. Now here's what's convenient about this. You guys notice they're all dB dt's? That's very convenient. And that's how we're going to get this problem solved. Remember, we're trying to find k. So I'm going to put these two together now. And I get 11 dB dt. And if I divide the dB dt off both sides, I'm left with my answer, k equals 11. So it was a little bit different than a typical related rate problem that we're used to solving in class, but a lot of the ideas were the same. Take a formula, find the derivative of it, plug some stuff in. Okay, so that's what k would have to equal in order for all this stuff to be able to hold through. So your number 1 on the College Board work for this week will be fairly similar to that. Let's take a look at example 2. This one is another related rate question. The first few problems are all related rate questions. This one I figured, has some elements to it that are a lot like your number 2. So let's take a look at it. The volume of a cube is increasing at a rate of 27 square root of 3 cubic feet per minute. Given that the diagonal of the cube is radical 3 times the length of the edge of the cube, find the rate of change of the diagonal when the length of the edge is 3. So we have a cube. Okay. What do we know about this cube? We know that there's a diagonal. Now, if you don't know what a diagonal of a cube is, it's the line that goes from the top left corner to the bottom right corner. Okay. And what they're telling me is that that length, which I'll call D, is the D is radical 3 times the edge of the cube, which we'll call X. I guess we could use E. Why don't we be consistent with letters here? We'll call that E. Radical 3 times E. So the diagonal of the cube is the square root of 3 times the length of the cube. So that's a useful little formula there that might come up handy later. Now find the rate of change of the diagonal when the length of the edge is 3. So what they want me to find, so going back to our steps, step 1, draw a picture. Step 2, identify the given rate. Here's my given rate. The volume of the cube. So the rate of change of the volume with respect to time is 27 square root of 3 cubic feet per minute. The rate that I want to find is the rate of the change of the diagonal. So that's dd dt. Now the next thing we want to do is write a formula, and I kind of jumped the gun on that. I already wrote it down. The formula we have is that the diagonal is equal to radical 3 times the edge. But there's another formula that we're probably going to want to use because they're talking about the volume of a cube here. The volume of a cube is equal to the edge cubed. Okay, however long the edge is, cube that and you get the volume, right? All right, so step 5 is to go ahead and take the derivative of these formulas here. So let's see. Now, since I want the formula that's going to connect V and D, notice I don't have a formula that actually connects V to D. I've got a formula that connects V to E, and I've got another formula that connects D to E, but I don't have anything that connects V to D. So, before I move on to step 5, just realized that's why we have two formulas. We want to put those two formulas together so I get a formula with D and V in it. So here's what I'm going to do. I'm going to take this formula over here and I'm going to divide both sides by square root of 3. So now I have the edge is equal to D over the square root of 3. Why do I care about that? Since I know that E equals this, I'm going to take that and plug it in over here now. And that's going to give me a new formula that connects V to D. So V is equal to D over the cube root of 3 cubed. I'm sorry, the square root of 3 cubed. So I took, and this is probably, I think this is the part that matches your guys' situation on your number 2 on the College Board work, is that you're going to have two different equations and you have to put them together to create a third equation that actually connects the variables that we care about. The variables that we care about are the variable whose rate we know and the variable whose rate we want, V and D. So I needed an equation that connects V and D. Okay, so now we're ready to move on to step 5, which is where we take the derivative of this thing. So if I take the derivative of V with respect to t, I get this. And if I take the derivative of this thing over here, it's a chain rule. So the derivative of the outside, this radical 3 here, sorry, not radical 3, power of 3, is you're going to put a 3 in the front, and then you're going to square it, right? Don't change the inside. Now we're going to take the derivative of the inside and multiply it. So the derivative of b over the square root of 3. Well, I'm going to rewrite this just to help you guys out a little bit because it looks confusing that way. But another way you can write it is like this. So when you're taking the derivative of a variable be multiplied by a constant, you just get the constant, right? But don't forget, since we're taking the derivative with respect to t, we also need to put d dt. Okay, so there is our total derivative. The derivative of the outside was 3 blank squared. The derivative of the inside was 1 over radical 3 times that derivative of d with respect. And now we're ready for step 6, where we just start plugging stuff in. So in step 6, I do know what dv dt is. It's 27 square root of 3. Next, I'm going to go ahead and simplify this other side here a little bit. I'm going to square that 1 over the square root of 3, which is going to give me 1/3, and that will cancel with this 3. So those two things cancel out, and I'm left with d squared. And then we have the over radical 3 here because of this thing, and then we have the d dt. Now mind you, d dt is what I want at this point, right? So I still need to figure out what is d. Still need to figure out what is d. So go ahead and put some parentheses there. I'm going to replace d with what d equals. All right, well, they tell us that the edge is 3. So if the edge is 3, what is the diagonal? Well, as you can see from up here in our original equation, the diagonal is radical 3 times the edge, right? So if I just take this little equation here and I replace the e with 3, we get that the diagonal is 3, radical 3. Well, we're almost there. Let's keep going. So we found all the variables that we need to plug in. All right, so if I square this, 3 squared is 9, and the square root of 3 squared is just 3, so you have 9 times 3, which is going to be 27. So here's what I have now. So if I wanted to solve for d dt, I'm going to multiply both sides by the reciprocal of this fraction here. So it cancels out on the right side there. 27's cancel, and then square root of 3 times the square root of 3 is 3. Oops. Why I'm having technical difficulties here. And we want to include units, so we're talking about feet and minutes. So this is, the diagonal would be in feet, and the time would be in minutes. So the diagonal is increasing at a rate of 3 feet per minute. Okay. So once again, I think what makes this problem a little different than the standard related rate question is that you have two formulas. You have one formula connecting the diagonal to the edge, and you have another formula connecting the volume to the edge. And we need to put those two equations together to create a new equation that connects the two variables that we care about. That's the main step. After that, all the steps are pretty much the same as all of our standard related rate questions. All right, let's move on to number 3. Suppose you're standing 7 feet away from the launch pad of a bottle rocket. The rate at which the rocket gains velocity is given by this. I think this is worded wrong. I think I meant to put gains altitude. I'll just put ALT here. The rate at which the rocket gains altitude is given by dHdt, feet per second. What is the rate of change of the angle of elevation in radians per second when the height is 24 feet? So let's start with step 1. Let's draw our picture. We have a bottle rocket right here, and we're standing over here, and this rocket is going straight up into the air. It says that we are standing 7 feet away from it. The height of this bottle rocket is represented by h. I don't know what the hypotenuse is. I'm not sure if we care about that in this problem. I don't think we really do, honestly. What it does ask us to do, well, let's follow our steps. So I think that's the end of our picture for now. Number 2, let's identify the rate that they give us. They give us the rate of change of h with respect to t. They tell us that that's 5 feet per second. Step 3, what rate are we trying to find? We're trying to find the rate of change of the angle of elevation. Now, if you don't know what that is, that's this angle right here. The angle between the ground and the hypotenuse here that goes up to the top of that rocket. So that's what we would call the angle of elevation. And so we're looking for the rate of change of that angle of elevation. All right, so I need a formula that's going to connect h to theta. How can I get h and theta in one formula? Well, by using trigonometry. This side is opposite. This side is adjacent. Opposite and adjacent is a tangent function. Now, I don't think on your guys' worksheet yours is going to be a tangent, just so you know. Hopefully you guys remember your SOHCAHTOA. Because I don't think the one on your guys' college example is a tangent. It's one of the other ones here. But you identify the sides. In this case, it's opposite and adjacent sides from this angle. And that, since it's opposite and adjacent, I know it's tangent. So that's how I figured that out. Now, let's continue. So tangent is opposite, which is h, over adjacent, which is 7. And so now I have an equation that connects the variable of theta, which is the rate that I want, and the variable of h, whose rate we know. Okay. Step 5 is to take the derivative of that. So what's the derivative of tangent theta? Well, that would be secant squared theta. And don't forget, we got to do the derivative of the inside, which is d theta dt. Now, h over 7, a better way to write that would be 1 over 7 times h. Okay, that way you would understand that the derivative is 1 over 7 times dh dt. So that's step 5. Now, step 6, we're going to start plugging some stuff in here. All right. Now, this is where things get a little bit interesting. First of all, I'm going to plug in dh dt. dh dt is 5. So, step 6 so far, I have the following. d theta dt. I don't know my theta yet, and in fact, I'm not even going to find theta. You'll see what I'm going to do a little bit different in a minute. But if I replace this piece with 5 and multiply it by 7, I get 5/7. Okay. Now, we're going to do something a little bit weird here. Instead of finding theta, what I'm going to find is I'm going to find secant of theta. Secant of theta. What the heck is that? Well, we talked about SOHCAHTOA, right? Now you'll notice that there's nothing in here for secant. Oops, this is supposed to be OA. There's nothing in here for secant. This is sine, this one's cosine, and this one's tangent. But secant is the reciprocal of cosine. So if cosine is adjacent over opposite, then secant is hypotenuse over adjacent. Okay, so it turns out we do need to know the hypotenuse of this triangle. I wasn't sure, but now I am. We actually do need to find the hypotenuse so I can find secant. Right? Now, since it is a right triangle in this case, we are going to use Pythagoras Theorem. We want to pay attention to the moment when h equals 24. Okay, and what I want to find is, we'll call this c, the hypotenuse. So we have 7 squared plus 24 squared equals c squared. This is 49 plus, I think that's 576 equals c squared. If I add these two things together, I believe we get 625. And then if I take the square root on both sides, I get 25. Okay? So now I know that my hypotenuse is 25. So what would secant be? Make some room here. Secant is hypotenuse over adjacent. So here's what we have then. D theta over dt. Instead of secant squared, we're going to put what secant is in there. What is secant? Secant is 25 over 7. Hypotenuse over adjacent. Now it's being squared because it's secant squared, right? All right. So now we have d theta dt, and this one's going to be 625 over 49. And then to solve for what I want, the d theta dt there, all I have to do is cross this off and multiply the reciprocal to the other side. And in this case, 7 goes into 49 7 times, and 5 goes into 625 125 times. And so we have our final answer there. And that is in radians per second. So d theta dt is equal to 7 1/25ths of a radian per second. So what made this one interesting is twofold. First of all, you had to know SOHCAHTOA to set up your formula. Second of all, instead of finding theta, we find the trig ratio instead using Pythagoras Theorem. Those are the two unique elements of this particular related rate question. All right. For example 4, I'm not going to do an example. I will give you a suggestion though. On this problem, you are going to have to use the product rule. And if you forgot how to do that, I would say go ahead and look back at example 1. I give an example of how to do the product rule there. Okay. For number 5, more related rate question. Man, really drilling this stuff. All right, a right triangle has a height of b, hypotenuse of c, and b is constant. But c changes over time. So we have a right, ooh, how that happened. We have a right triangle. The hypotenuse is c, and it's changing. But the height, that's not the height that I labeled, the height is not changing. It's b, it's just a fixed number. Now I'm going to label that. That's important. You'll see why that's important later on when we get in the problem. And I think that's what your example 5 has in it as well. It has a constant number. It has a variable, but that variable is not actually a variable, it's a constant. So we're going to treat it like it's just a number. And you'll see why it's important as we work through the problem. And we have this c is changing, and its rate is represented by dc dt. Now that's kind of why it's important, because the rate of change of c is dc dt. The rate of change of b, though, since b is a constant, is 0. So that's why it's important to identify that b is a constant. So that's an important element for you guys to pay attention to for this problem. Now, it says the angle between c and b, which we'll call theta, is given by this, which is totally rational. We know that. That's secant, which is adjacent over hypotenuse. I'm sorry, hypotenuse over adjacent. So there we have it. They want us to find d theta dt. So we have our picture. Here's the rate that we, I guess in a way, are given, okay? And they want us to find d theta dt, okay? Actually, I would say this is more like the rate, because we know that dv dt is 0. I don't know. Let's work it out and see what we get. So let's do this. Let's find the derivative of our little formula here. Now, secant theta, the derivative of that is secant theta tangent theta. Hope you guys are using your flashcards that I gave you. Now, this is an interesting situation here. We've seen this a few times on previous problems. Like we saw this on the last problem, right? The first thing I did was I rewrote it. So it looked like this. And then we took our derivative of it. And we got 1/7. The constant stayed there. dH dt. Remember that in the last problem we did? Well, actually, it doesn't look like that's what we're going to do here, but it is. Usually, if I saw two variables here like this, I would do quotient rule, but I'm not going to, because that b is actually not a variable, it's a constant. We just don't know what it is. So it's 1 over b, and c is our variable, right? And so when we take the derivative of that, it's going to become 1 over b dc dt. Oh, and I forgot on this side, when you take the derivative of secant, you need to multiply the derivative of the inside, which is derivative of theta. So there's our derivative. We did the derivative of secant, which is secant theta tangent theta. The derivative of the inside of the secant, which is d theta dt. That's equal to the derivative of the right side here, which is 1 over b times dc dt. So there's our derivative. So that's step 5 of our related rate process. Now what are we gonna do? My goodness. Okay. So I just remembered what makes this problem kind of a weird problem. It's the fact that they're not really giving us any numbers and everything is in letters. It's kind of a pain in the butt. So, here's what we're going to do now. We're going to find this other side down here. Let me call it x really fast. A lot of this process is actually quite similar to the last problem we did. It's just that instead of having numbers, we're going to use letters. Now, okay, for those of you guys watching this movie, or this video I'm making, some of you guys got the remind where I was saying homework's due tonight, but it's not, it's due tomorrow. And I just fixed that, but I'm getting like my phone blown up with like hundreds of people saying repeatedly, "You gave me a heart attack." I'm so sorry. Okay. Anyway, back to this problem here. We need to find this third side. Now the third side, according to Pythagoras Theorem, we don't want to use the x. We don't want to create a new variable. We only want to use the variables they have for us. So I'm going to find this third side here in terms of b and c. So using Pythagoras Theorem, I would have b squared plus x squared equals c squared, right? Now I want to get the x by itself. So I'm going to move the b squared to the other side, minus b squared. And then we're going to square root both sides, right? And that's what x equals. So this side over here is the square root of c squared minus b squared. All right. Now let's go ahead and we're going to do a lot like what we did in the last problem. We're just going to be replacing the sine and the tangent with what those things equal on the problem here. So d theta dt, what would sine be and what would tangent be according to this triangle that we're looking at over here? Well, tangent is opposite over adjacent. So that would be, this is opposite from the angle, this is adjacent. So tangent would be the square root of c squared minus b squared over b. Secant is hypotenuse over adjacent. Okay, so now we're going to go ahead and we're going to simplify this a tad bit. I'm going to multiply these together. Not going to look very impressive. It's going to be c square root c squared minus b squared over b squared. Okay, so now the last thing we want to do is we want to figure out what is d theta dt. So I need to get this piece by itself, and the way we're going to do that is by taking this off this side and putting it over here as a reciprocal, right? Multiply both sides by the reciprocal is the rule. The b's cancel, and here's my final answer. We end up with 1 over c square root c squared minus b squared dc dt, and that's it. So that's all they wanted on this question. So I'm sure that was more than enough. If you were kind of confused on this question and you haven't done number 4 yet, go back and watch the part for number 4, though. It'll help make this a lot more sense because this one is the same thing. It's just with letters instead of numbers. All right, example 6. So given that f prime of x is equal to x squared plus 4x minus 3, and f of 4 equals 8, find an approximation for f of 4.5 using a tangent line at x equals 4. So just to give you guys a little bit of background here, you don't need to draw this part, but basically when you have a curve, a tangent line, the line that touches your curve at a single point, is the closer you are to that point of tangency, the tangent line is a very good approximation of what the actual curve is. It has almost the same slope, and it has almost the same y values at that point. And when you actually get to that point, they're exactly the same. But the closer they are to that point, the more approximately correct they are. And the further away you get, as you can see, the tangent line is no longer anything like the actual curve. So the closer you are, the better. The farther away you are, the less inaccurate it is. I don't know. I think I might have said that backwards, but hopefully you guys got the idea there. So that's what I mean by a tangent line approximation. So we have a derivative given to us. We don't know what the original function is, but we do know of a point on that original function. The point is 4, 8. Now we want to estimate what f of 4.5 is, and we're going to do that using a tangent line. So the first thing we need to do then is we need to find the equation of our tangent line. And in case you guys forgot, the way you find the equation of a tangent line is with the point slope formula. Way back, learned that in August. You need an x value, you need a y value, and you need a slope. The x value and the y value are pretty straightforward. They're 4 and 8. The 2 points where the tangent line touches the function. The slope of our tangent line at that point, well, the slope of my tangent line at x equals 4 is going to be the same thing as the slope of the function at x equals 4. Well, here's the derivative of the function, and the slope of my function at 4 is going to be the derivative of my function at 4. So I just need to plug in 4 to my derivative there. That's going to give me 4 squared plus 4 times 4 minus 3, which is 16 plus 16 minus 3, and that's 32 take away 3, which is 29. So I guess my slope is 29. That's a pretty steep slope. Now I can plug in my numbers to my point slope formula. So y minus y1 is 8, m is 29, x minus x1 is 4. And from here, we can just distribute, I guess, and move the 8 over to get it in the slope-intercept form. It's not extremely necessary, but I'm going to go ahead and do that. So this would be 80 plus 36, which I believe would be 116. And then we're going to add 8 on both sides. And we end up with y equals 29x minus 108. So that's my tangent line. And we're going to use the tangent line to approximate what f of 4.5 is. Now, 4.5 is pretty close to 4, right? So this point that I'm estimating, since it's really close to the point of tangency, my tangent line should be able to give me a pretty good answer for what f of 4.5 is. So f of 4.5 should be approximately equal to y of 4.5, which means that it should be approximately equal to 29 times 4 minus 108. Okay, so once again here, getting 80 and 36 is 116 minus 108, which is going to be 8. So we would say that f of 4.5 is approximately y of 4.5, which is 8. On example 7, I just want to say that there's a little bit of a typo. I'll show it to you. I'm not supposed to show these problems on YouTube, but they have a typo, so it's kind of their bad. So I'm not going to differentiate this problem. I'm not going to actually do the problem for you, but I will say that one of these was supposed to be f prime, and I'm pretty sure it would be this one. Let me double check to be sure. Yeah, so it's this one that's supposed to be the derivative. So they just had a typo there. But other than that, I'm going to let you guys do it because it's pretty much just like the last one. Example 8, very similar as well. So if you need help with those, I would refer you back to example 6 just so you know how to find a tangent line and use that to make your approximations. Other than that, I would say just see me during a Zoom if you don't know how to do those. It's pretty straightforward though. Let's go ahead and take a look at example 9. Now in example 9, you guys are asked to find the derivative of a function that actually has an absolute value. So if I wanted to find the derivative, sorry, let me undo that. If I wanted to find the derivative of this, you could turn it into a piecewise function. It's not really necessary though. We can use an old rule that we talked about a while ago. If you have the absolute value of f and you want to find the derivative of that, basically what you could do is you could just write f over the derivative, sorry, the absolute value of f times the derivative of the inside. So that's our shortcut for taking the derivative of an absolute value function, and that's the one I'm going to use here. So if I wanted to take the derivative of this, I would get 5x minus 3 over the absolute value of 5x minus 3 times the derivative of 5x minus 3, which is 5. Okay, plus, now we need to do the derivative of 8x squared, that's 16x. Now, if you wanted to find the derivative at any point, like let's say 2, well, all you'd have to do is plug in 2. And that's it. It's that simple. 10 minus 3 is 7 over 7. That's just going to be 5. And I would end up with 37. So that's how you find the derivative of an absolute value function. Okay. Now, last week, we dealt with these, and I said change it to a piecewise function, which you could do that. But if you're just being asked to find the derivative at a specific point, then just use this rule. Okay? If you're being asked to prove that it's differentiable everywhere, that's when you would want to break it apart into a piecewise function and do the whole limit from the left and limit from the right thing. But in this case, just use the formula, a lot easier. All right. Let's go ahead and continue on here. For numbers 10 and 11, I'm not going to do any examples for you necessarily, but I just want to talk about what continuity and differentiability looks like on a graph. So continuity just basically means connected, no holes, gaps, or jumps, and differentiable just means smooth. So for instance, this graph is continuous everywhere, but it's not differentiable here because that corner is not smooth. Okay. Here's an example of a discontinuity. Because I've got a hole in my graph, those two pieces are not really connected. They have a gap between them. And so it's not continuous. And just so you guys know, if a function's not continuous, then it won't be differentiable either. Okay? Because in order to be differentiable, a function has to be continuous. So there's a couple ways a function may fail to be discontinuous. One is with a hole. It could look like that, or there could be a dot above it. It doesn't really matter. That's still discontinuous. Another way is with a jump. That's another discontinuity. And another type of discontinuity are vertical asymptotes, so things like this. Okay, so those are discontinuities. And since they're discontinuities, those are all examples of places where a function is not differentiable. This is the one thing that's a little bit unique, though, because even though it is continuous, it's not differentiable. Okay, so that's pretty much all I have to share with you guys about differentiability and continuity when you're looking at graphs. Oh, I guess here's another. I found another example actually of something. Let me see. So we said that this was an example of continuous but not differentiable. There's another example of a function that is continuous but not differentiable at a certain point, and that would be things like this. I didn't draw it very well. Let me start over. Places where your curve have a vertical tangent line. When you have a vertical tangent line, the slope of that line, which is the derivative, which is differentiability, the derivative is undefined, which means it's not differentiable at that point. So even though that curve is connected, it's not differentiable. An example of a function like that would be like y equals the cube root of x. The cube root of x does that, okay, where it has a vertical tangent line. That's another example of a function that's continuous but not differentiable. All right, moving on here. Number 12. To help you out with number 12, I'm just going to ask the question, where is this function not differentiable? Well, first of all, I want you guys to notice that it's continuous everywhere. There's no, well, I guess that's not entirely true. Anywhere where this function would equal 0, or something less than 0, it would not be differentiable at that point. So let's figure that out. So because, oh, wait a minute, I take that back actually, because it's absolute value, right? So no matter what you get in here, you're always going to get a positive number or 0. So you're always going to get a good answer for the square root. That's the only way that a square root function may end up with some kind of a discontinuity, is if you end up with a negative underneath of the square root. But that's not going to happen since we have the absolute value bars. So this function is continuous everywhere. Remember, if you want to tell if a function is differentiable, you have to look at the continuity first. Because if a function is not continuous, then it's not differentiable. But now we're going to move on to see if it's differentiable. To see if it's differentiable, what we're going to do is we're going to take the derivative of this thing. So, first of all, let's take the derivative of this function. Now, this is a chain rule. It's actually a double chain rule. The derivative of a square root is 1 over 2 square root of whatever we had originally. But we need to multiply this by the derivative of the inside. Now, the inside is an absolute value function. We talked about that on the last problem. On the last problem, we saw that the derivative of an absolute value is whatever's on the inside divided by the absolute value of whatever's on the inside. Finally, we need to take the derivative of the inside of the absolute value, which is 2x plus 5. Now, in looking at all of this, is there anything that is not allowed? In other words, is there something that x is not allowed to equal? Up here, x could be anything, because the absolute value bars just made everything 0 or positive, which is okay for square roots. But in this case, we have a problem. The denominator cannot equal 0, and it's very possible that these absolute values turn out to equal 0. These absolute values would equal 0 if x squared plus 5x equals 0. So what values of x will make that happen? Well, you have to factor it first, and you set each piece equal to 0. So x equals 0 is one place that will make the bottom equal 0, and x equals -5 is another number that will make the denominator equal 0. So even though the function is continuous everywhere, it's not differentiable at 0 and 5, because when I take the derivative, I end up with a function that has denominators, and anytime you got denominators, the denominators can equal 0. So those two values of x are the two values of x that would make the denominator 0. Therefore, the function would not have a derivative at that point, and therefore it's not differentiable. Okay, so in summary, what do we do to find out where a function is not differentiable? First of all, you have to look at the original function and see if there's anything that x is not allowed to equal in the original function. Now, first here I got a little stuck because I thought square roots have limitations on them, but the absolute value kind of nullified that. So it was continuous everywhere. Then I found the derivative, and then I asked the same question. Are there any limitations on what x can equal here? And the answer was yes, it was here and here. So the function is not differentiable there. So you have to check continuity first, and then differentiability. Okay, moving along to number 13. The question for this one was, we wanted to find a value for a and b that will make this function continuous and differentiable. So let's go ahead and focus on the continuous part first. First of all, this is cosine. Cosine is continuous everywhere. This is a linear function. Linear functions are also continuous everywhere. The only problem, therefore, where we might have a discontinuity is where those two pieces are connected, and that's at 0. So I need to make sure that the limit, as I approach 0 from the left, is the same as the limit as I approach 0 from the right. Now, if I'm approaching 0 from the left, that's the top piece. And if I'm approaching it from the right, that's the bottom piece. And I need those two things to come out equal in order for this function to be continuous. That means if I'm approaching the same number from the left as I am from the right, that means the two pieces are connected. So if I plug in 0, I get 1. And if I plug in 0 here, I get b. So now I see that b has to equal 1. Now the next thing I'm going to do is I want to make sure that it's also differentiable. Now to make sure that it's differentiable, what I'm going to do is I'm going to take the derivative of this function. The derivative of the top is negative sine. The derivative of the bottom is a. And we're going to do the same thing. I want to make sure that the slope from the left of 0 is equal to the slope from the right of 0. That if the slope from the left and right are the same, then they are connecting at a smooth curve, and therefore it's differentiable. Okay? Now if I'm approaching from the left, it's sine x. And if I'm approaching from the right, it's a. And in order for this to be differentiable, I want them to be the same on the left and right. So we do our direct substitution, and I get 0. And here, if you plug in 0 for x, well, there is no x. You just have a. So now I see that a is 0 and b is 1. Now this was an easy problem. I don't know if your guys' would involve the difficult part. Sometimes when you do this, instead of just getting the answer right away, you get an equation here and you get an equation here. And you have to put those two equations together to solve for A and B using substitution or elimination or something like that from Algebra 2. I'm not too sure if yours has that. I don't think it does, but it's a good skill to have. But anyway, it's not on this one, so give yours a shot, see what you can do. But that's the idea. All right. Let's go ahead and move on to number 14. My only suggestion for number 14 was to see the FRQ video for this. I think it was on part B. So just look at part B. If you do part B of your FRQ, and I've already made a video for that, check that out if you need help with it. But if you know how to do part B on the FRQ, then you'll know how to do number 14 here as well. Okay, let's go ahead and move on to number 15. Number 15 says, let cosine of x equal y. We want to prove that y equals cosine of x is a solution to this differential equation. So you have a problem kind of like this on yours. Now, what does that mean? To me, it's just kind of a weird thing. What does it mean to have a solution of a differential equation? It means that we know what the y value is, basically. So they want to know, is this y value, cosine x, is that a solution to this differential equation? Now, as you can see, we're going to need y, which we have, but we're also going to need y prime, y double prime, and y triple prime. And at the end, it should come out to make 0. If it doesn't, then we've done something wrong. So we know y equals cosine x. Y prime is negative sine x. Y double prime is negative cosine x. And y triple prime would be sine x. So if I plug all these in, I'm going to replace y with cosine x. I'm going to replace y prime with negative sine x. I'm going to replace y double prime with negative cosine x. And I'm going to replace y triple prime with sine x. And the question is, does this make 0? And yes, it does, because negative sine cancels positive sine, and cosine cancels negative cosine. So we're left with 0 equals 0, and it checks out. If we didn't end up with 0 equals 0, then, or the left side equaling the right side, then that would mean that this is not a solution. But it is, so we're good to go. So that's basically it. Let's go ahead and try another example here. So your example for 16 is a lot like what we just did in number 15. It's just that we're going to have an extra task at the end where we have to solve for the k at the very end. So first of all, we need y prime, and we need y double prime. So y is equal to e to the negative 2x plus e to the 3x. Y prime, if you take the derivative of this, you're going to get e to the negative 2x again, but you multiply the front by the derivative of the power there, which is going to be negative 2, plus, same thing here, 3e to the 3x. And then y double prime is going to be the same thing. You get e to the negative 2x again, but you're going to multiply the front by the derivative of the power again, so you get 4 plus 9e to the 3x. And so now what we're going to do is we're going to go ahead and plug all of these things in for y, y prime, and y double prime. So we have negative 2 times y plus y prime plus y double prime equals 2k e to the 3x. Running out of space there. All right. So I'm going to plug y in here. Y is e to the negative 2x plus, back up a little bit, e to the 3x. Y prime is negative 2e to the negative 2x plus 3e to the 3x. And then y double prime goes here, which is 4e to the negative 2x plus 9 to the times e to the 3x. All right, so first we're going to go ahead and distribute this in here. And we're going to get negative 2 e to the 2x minus 2e to the 3x. And we can pretty much just get rid of the parentheses everywhere else. Okay, and then we're going to combine all the like terms. Now, here's a e to the negative 2x, here's another e to the negative 2x, and here's another e to the negative 2x. Negative 2 and negative 2 makes negative 4, and negative 4 with positive 4 makes 0. So these three things just cancel each other out. Oh, I think I crossed off the wrong thing. Let me back up. These three things cancel each other out. The next thing we're going to look at is we're going to combine all the terms that have 3x's in them. I'm sorry, e to the 3x. So this one has negative 2. If you add that to 3, you end up with 1. And if you add that to 9, you get 10. So we have 10 e to the 3x equals 2k e to the 3x. And in this case, we're just going to divide both sides by e to the 3x. And so we're left with this very simple equation here, 10 equals 2k. If you divide both sides by 2, you end up with k equals 5. There you have it. Moving along. So for examples numbers 17 through 19, I just want to illustrate a few things for you guys. I'm not going to really do too many examples per se. Take a look at, that's one of your guys' problems, but I'm not allowed to do it. So let me take a look at a few others. So these are slope fields. And in case you guys forgot, a slope field is what you would get if you had a function, kind of like, say, this guy here, right? And basically, you would plug in any number you wanted to for x and y. Like, if you wanted to find what's the slope going to be at the point 0, 1, you would plug in 0 for x and 1 for y. And at 0, 1, it should have a slope of 0. And so which of these graphs up here would have a slope at 0? A slope of 0 at the point 0, 1. So we plugged in 0, 1, that's the point. Which of those graphs up there have a slope of 0 at that point? A flat horizontal line. It's kind of hard to tell because they didn't really label their x-axis, so I don't really know exactly where one would be at. I'm not real sure. I'm thinking that it possibly could be, gosh, it's kind of hard to tell just by looking at this one. Pondering. There's a couple of them up here that have a slope of 0 at 0, 1. Like here, this one has one. This one has a slope of 0 at 0, 1. This one probably does as well. This one definitely does not. This one does not. This one looks like it may actually. Can't really tell where it's at, but it's somewhere in there. So we've narrowed it down to these 4. Another thing you could look at is you can look at the signs. So for instance, anytime both x and y are positive, you should get a positive slope. Or if x and y are both negative, you would get a positive slope. So for instance, over here, in this quadrant, x and y are both positive, so all the slopes should be positive, but they're not. So that's not the option. But this one, in this quadrant, all the x's and y's are positive, so all the slopes should be positive. So that looks good. It should also apply, however, when both of them are negative. In this case, these are negative slopes, so that doesn't work. Down here, since you have a negative over a negative for the slope, you should end up with positive slopes down here. That's no good. This one is good. We've got positive slopes here and here. This one, no. And so we've got our answer. So that's one type of question that you could do with these. However, there's two types of questions you could do with these. One is matching the graph to the derivatives or the differential equations. But a lot of the ones that are on your work for this week are different. A lot of the ones that are on your work for this week are matching the graph of the slope field to the original equation. Okay. Now, here's what I want to point out to you guys about doing this type. To be able to match the graph to the equation, you kind of have to know what functions look like. So for instance, suppose I picked a point right here. Well, if you did the FRQ for this week already, what we talked about is you could sketch the solution curve in this slope field by kind of imagining that those lines are kind of like currents of water, and the dot is like where you just dropped a twig in the water. Where would it go? Well, as you move to the right, it would flow up like this, and as you move to the left, it's going to flow down like that. Okay. Now, is that the graph of that graph should match these functions? This is a constant function. Is that what constant functions look like? No. This is a linear function. Is that a linear function? No. Is that a quadratic? No. Could it be a cube function? Maybe. Cube functions do kind of look like that. Does that look like a sine function? Sine waves look like this, so no, that's not it. Ln functions, ln functions look like this. Since there's an absolute value, it'll also look like that, but that's kind of going a little bit beyond what we need to focus on right now. So no, that's not it anyway. Cosines look like sines. These guys here, a lot of you guys probably don't remember what those look like, but they look something like this. So that's a no. So really the best answer possible is that. How about number 1 over here? What if I dropped a dot right here? Well, if you sketch the solution curve, it's going to look something like this, right? Follow those slope markings. Which curve could that possibly be? Well, that would either be a sine or a cosine, right? So how do you know which it is? Well, a good way to tell is by just picking a point and plugging it in. So for instance, let me clear this up a little bit. I'm going to use a point that we know well, 0, 0. It's going to look something like this, right? All right. Now, at 0, 0, if I were to plug in 0 for x, I should get 0 for y. Okay? So which function would do that? Would cosine do that or would sine do that? Plug in 0 for sine, you get 0. But if you plug in 0 for cosine, you get 1. So when x is 0, cosine should be way up here at 1. That's not accurate. So it's not cosine. Sine is the one that starts at 0 and goes up and down. So there's your answer. So basically, if you can match the shape to the curves, then the curves of the shape to the equations, then that's one way to do it. But sometimes you got to get a little bit more specific and just after you make your curve, just pick some points to plug in and see which equation will satisfy those points you're plugging in. I only did one, but you could do a few. Okay, there you have it. So that's my suggestion there, how you can match a slope field to the particular solution. And that's what you guys are asked to do on a couple of questions. Well, we got one more thing we want to look at here. And these questions, guys, I can't emphasize it enough. These are very important. So if anything this week, I would really just make sure you guys know how to do numbers 20 through 25 really well. I can almost guarantee you they're going to ask you a question like that on the FRQs this year. And usually with these types of questions, they just rack up the points. You get a lot of points for these. You get a lot of bang for your buck. They're not easy, but they have a lot of algebra in them. But they're really worth sitting down. And after you do a couple, you kind of realize they're all very similar in the steps they have. Now, if you don't remember how to integrate very well, you'll have some more hardships because different problems might have different integration tactics involved. But the general process of how to do this, if you just kind of set the integration part aside, it's almost the same on every problem. There's a lot of steps, but those steps are almost always the same. The only thing that's different is really the integrals. So you have to know your integrals to be able to do this. All right, so what we want to do is we want to find a particular solution for this differential equation with this initial condition. And once again, how do you find a particular solution of a differential equation? That means they want to know, what does y equal? If the derivative of y with respect to x equals this, then what does y equal? Okay, so the first step is going to be to separate the variables. Okay, so what that means is we're going to leave the dy on the left side, and I want to put the dx on the right side. And I want all my x's on the right, and I want all my y's on the left. So the only y that's over here on the right side is right there. So what I'm going to do is I'm going to divide both sides by y to get rid of it over there. And now I have this. And on the right side, we have the rest of the problem there, which is 2x over the square root of x squared minus 16. Now that's a very simple first step. Just separate the variables. Right there on these FRQ questions, that alone is worth 1 point. Please don't miss that point. Very simple one to get. All right, now the next thing we're going to do, and this is where things get a little bit tricky, okay? You have to know how to integrate. Step 2 is to integrate. No, you don't get a point for just writing that. You actually have to integrate to get the point. So, and matter of fact, for this one, you get a point for integrating each side. So you get 1 point for this side and 1 point for this side. Now the left side is really simple. That's just a log problem. The right side is not so simple. So, what I would encourage you guys to do is sit and ponder for a minute, maybe pause the video and think about how would you integrate that? We just got through with integration review last week, or maybe 2 weeks ago now. See how well you can integrate that. What would you do? Pause the video if you need time, but I'm going to go ahead and say the answer now. What you would do is you would do u substitution. The u is x squared minus 16. The derivative of u with respect to x is 2x, and therefore that means that dx is equal to du over 2x. So if I do some u substitution, I'm going to have the following. And conveniently, those go away. So now I'm left with the integral of 1 over the square root of u du, and I'm just going to rewrite that as u to the negative half. It's a half power because it's a square root, and it's negative because it was in the denominator. And now we're ready to use the basic power rule that we've known for a while. So add 1 to the power, you get a half, and divide by half. Now dividing by a half is the same thing as multiplying by the reciprocal of half, which is 2. So I'm just going to put times 2. And don't forget your plus c. At this point, well actually not quite at this point, because we've got to get rid of the u first. But after that, you would have gotten 2 more points for just doing the integration. And if you only integrated one side, well, you stopped early, you're not going to be able to finish the problem. But if you at least got the left side, then that's another point. You would have gotten 2 points for just getting that done as well. But let's go ahead and finish this. So we have ln of y is equal to 2, and u was x squared minus 16. Half is a square root, and I just replaced the u with what u was, which is x squared minus 16. Don't forget your plus c. Okay. Now the next thing that we need, so that there, we're up to our third point. You get 1 point for finding the integral of the left and 1 point for finding the integral on the right. So we're up to 3 points now in this problem. Mind you, an FRQ only consists of 9 points. So this one question out of the 5 questions that are usually there is taking up almost half of the points for that FRQ. Very much worth it. Okay, now at this point, what I would say you should go ahead and do is plug in your initial condition. Okay, so I'm going to go ahead and I'm going to plug in the 5 for y, and I'm going to plug in the 4 for x. Now 4 squared is 16, and 16 take away 16 is 0. The square root of 0 is 0 times 2 is 0. So here's my c value. C is ln of the absolute value of 5. We really don't need the absolute value bars though, because 5 is just a normal number, so we'll just leave it like that. Okay, so that there would be worth another point. Plugging in your initial condition. Matter of fact, even if you don't find C, I've seen them sometimes just give points for just plugging in the initial condition sometimes. But I would say let's kind of wager on the safe side and say you need to find C to get that 4th point. Okay, but now that we know what C is, we can go ahead and plug in the C. So now I have ln of y is equal to 2 square root of x squared minus 16 plus ln of 5. Okay, the last point for this is to get the y by itself. Okay, it's pretty simple, and I'm pretty sure you're going to get credit if you just do one simple thing with this. You have to know how to get y by itself. Now in this case it's not too bad. It's just not, it's hard to remember, but if you remember it, what do? Basically you exponentiate both sides, and what that means is you make both sides an exponent of the base e. So it's going to be e ln of y is equal to e 2 square root of x squared minus 16 plus ln of 5. Now these two things cancel. And I'm left with this. The absolute value of y is equal to e 2 square root of x squared minus 16 plus ln of 5. Now, we don't need the absolute value bars because this is an e function. Exponential functions are always greater than 0. Now, the exception would be if there was a negative in the front here. That would change everything. Now the function would always be negative. But without the negative, exponential functions are always greater than 0. And if you don't need to write this, but just to help you understand that, exponential functions either look like this or they look like this. But they never go into the negatives for the y values. So since we're taking the absolute value of y, this side's positive, so it doesn't matter what y is. Y is going to be positive anyway because the right side is always positive. So there you guys have it. We don't really need the absolute value bars in this case. Now, next thing we're going to do. Now, honestly, at this point, if you had an FRQ, I would say just stop here because this is good enough. But on your multiple choice for this week, we're going to take it a little bit further because you can make it look a little bit simpler. So a while back, we talked about these. And what we're going to do is we're going to start by rewriting this like this. Instead of having 2 powers being added, we're going to rewrite that as 2 e's with those powers that are being multiplied together. Now, why would I do that? because this can be simplified. The e and the ln cancel, and you're just left with 5. So now we have this. And this is really the simplest way to write your answer. There you go. Okay. Now, if I'm not mistaken, one of your questions on this College Board assignment is going to ask you guys to find the domain, I believe, of your function. And that means just what is x allowed to equal? What is x allowed to equal? In other words, are there any restrictions on x? Well, square roots can't have negatives in them, right? So x squared minus 16 always needs to be greater than 0. So first of all, we're going to add 16 to both sides. And then we're going to square root it. Now, as you guys remember, when you square root, you get a positive answer and you get a negative answer, right? So the square root of 16 is 4, so we get 4 and negative 4. But here's something kind of interesting. For the one that's positive, it looks like this. X is greater than 0. But with inequalities, whenever you get a negative answer in this fashion, you end up reversing the inequality. So here's your domain. X would have to be less than negative 4, and it would also have to be greater than 4. Okay? So whenever you solve an inequality by taking a square root, you get a positive and a negative answer. Of course, like always, the negative one, though, you flip the sign. The positive one, you keep the same. And I don't remember if the next fact I'm going to share with you guys, let me, before I say that, let's just back up. This is what we call the domain, and that is what x is allowed to equal. In other words, x can only equal numbers that are greater than 4 or less than negative 4. That's what they mean by a domain. So what can x? Now, let's see. Next question. I think it can equal 4 as well, because over here, by the way, you can get a 0 for an exponent. That's okay. It wouldn't be differentiable at that point because you can't have 0 in the denominator. But I don't think that it has to be differentiable at that point. It just, so x can equal 4. There's no reason it can't. So I would say the domain would be x is greater than or equal to 4, or x is less than or equal to negative. But anyway, something else that might come up while you guys are looking for your domain is I think you might have an equation that's like this. It's like backwards or something. So let me come up with a better example. Like, let's say I had this, right? First, you would minus 9 on both sides. But before I take the square root, I need to divide by a negative 1. Anytime you divide by a negative, that also reverses the inequality. Okay, so if you divide by a negative, that reverses the inequality. And don't forget, we're going to square root that 9, and we're going to get a positive 3, and we're going to get a negative 3. And for the negative 3, we're going to reverse it again. Okay, so there are two times whenever you're going to flip an inequality in the process of solving. One is if you're dividing by a negative. The other is if you're taking a square root. The negative one flips the inequality as well. So that's a little algebraic reminder there that I think will come in handy for your work. I think I had one more example I wanted to do with you guys here. Here we go. Let's go ahead and do this one. Find the particular solution for the initial condition. And by the way, I'm only going to do 2 problems. If you can do these 2 problems, you should be able to do all of the problems in 20 through 25, technically. But anyway, let's do part B now. So how do we do it? Step 1, separate the variables. I'm going to bring the y to the left side, by multiplying both sides by y, and I'm going to bring the dx to the other side by multiplying both sides by dx. Next, I'm going to integrate. I know at some point you guys are going to see a problem that looks like this. That is literally the same thing as what I just had. If there's no number in the front, you can assume it's a 1. Okay, so just be aware of that. Now, let's go ahead and integrate this side. If I integrate the left, I get y squared over 2. And on the right side, I get just x. And don't forget your plus c. We only need 1 plus c on the right side. We don't need a plus c on both sides. All right, so right there, I've already earned 3 points. I separated the variables. I integrated the left. I integrated the right. Now, we're on to the fourth point, which is to find our c. So I'm going to plug in my initial condition. I'm going to plug in -3 for y. I don't like writing that. Let me change colors real quick. So I'm going to replace the y with -3. And I'm going to replace the x with 0, which is just going to be c. So I end up with c being 9/2. Okay. So we now have y squared over 2 is equal to x plus 9/2. All right. Now we want to get our last point, which is getting the y by itself. So I'm going to multiply everything by 2 first. The 2's cancel here, the 2's cancel here, and we are going to be left with y squared equals 2x plus 9. And the next thing I'm going to do is I'm going to take a square root. Now remember, when you get a square root, you get a plus and a minus. So now this is the whole reason I'm including this particular example. There are 2 possible outcomes here, okay? Y is either y equals the square root of 2x plus 9, or y is negative 2x plus 9, right? And the question is, which one is it? And the answer is, it depends completely on your initial condition. Take a look at your initial condition. Which one of these equations, if you plugged in 0 for x, would give you a -3? Well, if you plugged in 0 up here, you're going to get, that's going to go away. You're going to have 9, and the square root of 9 is 3. That's a positive 3. We don't want that one. If you plug in 0 here, you get the square root of 9, which is 3, but there's a negative in the front, so the answer is -3. So this is the one we want. So sometimes, whenever you have those problems where you take a square root and you get a positive and a negative, to know which answer is the correct one, you have to look back at your initial condition. Okay? And there you guys have it. That's the end of it.